Welcome back. This time I want to create a user interface for our Mandelbrot renderer. And to do that, we create a new project, and we start by creating a new compose multi-platform project. I'm using the desktop version because it's easier to work with. I also copied in the code from our earlier episode, and I will start with cleaning up some of the code. We will remove the old main method. We don't need that anymore. I don't want any dependencies on Java, so we remove that. And we also don't want to render to a buffered image anymore. And now we can start creating our new code. I don't want this button from the template. I do want to give our window some properties. For example, we give a title and give it a size. And by that, we should have an empty window of size 300 by 300 pixels. And now we can create a new GUI component for rendering our Mandelbrot image. So let's call it an image canvas. That will take our image as an parameter. And it should be of type image bitmap. And as usual, we also want to take a modifier as a parameter with a default value. And in here, I will just use a canvas to render our image with draw image. And the image itself, I want to create as a value that we will get from a function. Let's create the function. And we will need the size of the canvas itself, which will be in size, I guess. And it will return image. And let's create some memory to store our image in that byte array of size width times it times 4, since we have 4 bytes per pixel. The data, we also need some image meta info from image info object, which will take the width of and the height of the image we want to create, and the color type I want to have type RGB 88X, and I want it to be Jetpack image, and then we can return image, make raster the info and the bytes, and we also need to give it the size of each row, which is the width times 4. And then we convert it to a compose bitmap. So if we first give it a size here, let's say 300 times 300, it's not the correct size since we have borders and stuff on our window. And this should also be a composable. And if we run this now, we have painted our image, which right now is just black. So let's plug in our Mandelbrot function instead. And we will do here for each byte, for each pixel on the width and height. So create this extension function that takes in the height and the width and the height of our image. And for each pixel, we will render the color of that pixel. We do it by saying looping over the width and the height, which is y. So this will loop for each pixel from 0 to just 1 below the width. And we will convert this to a value between 0 and 1 by saying the x value will be x divided by width minus 1, since we only go up to width minus 1. And we want it in doubles. We do the same for y, but on the height. And then for these values, we will find out the color. And we will get the color from some function that takes the x and the y values. And when we do have the color, we will add it to the byte array, this byte array, then offset. +1 and +2, because we will have the color, the red value of the color, and the green value of the color, and the blue value of the color. And the offset is calculated by taking the x plus y times the width, and we will time 4, since we have 4 bytes per pixel. This f function will also be a parameter to our function, and it will be a function, so that will have the type of taking double y and returning color in the form of an int. The color components RGB, we can calculate by making some extension properties on int. So R will be a byte we get. So we take the byte and shift it right 16 positions and convert it to a byte. That's the way we get the red component, and similar for the green and the blue, but instead we shift it 8 positions and 0 positions. So this function will be our Mandelbrot function. So the last parameter is a lambda, takes an x and a y, and returns our Mandelbrot function with the x and the y. And running this now, we should get our Mandelbrot rendered, but it's still zoomed in, so let's zoom it out completely. We'll remove this old scale that we had and replace it with a zoomed out version. There we have it, the zoomed out version of the Mandelbrot. And we could stop here, but I do want to fix some things first. For example, if we resize the window, the image is just painted in the top left corner. And I would like it to actually always be centered and also scale when I resize the window. But before we do that, I want to separate out our code into a view model, so we can separate the GUI code from the code that do the actual rendering. So let's create a view model. And we will move our image into the model and make it private. And to access the image from our GUI, we have to give it a handle, and we do it with a state flow. So private value, let's call it image as a mutable state flow, which will contain our initial image like that. And then publicly we will give it a image of type state flow. Of image map, and that will be the same thing as image. We also need an instance of our view model, so we can create it just somewhere outside our function. So value model equals a new Mandelbrot view model, and inside our GUI we can get a hold of it by saying like our image is the view model, model dot image. We collect it as state, and the value of that will be the image. If we just run it, see it still works. Nice. The next step is to capture the size of our canvas inside our image canvas. So we add to the modifier on size changed And whenever the size is changed, we call our own size changed method with the argument that we get this on size changed. It's an int size with the new size of the canvas. And this on size changed is just a method that we provide to the as an argument, and it will be of the type an int size, and it just to return nothing. In our call to the canvas, we will replace this with something from the model dot on size changed, and it will be a lambda that just takes it, and we create it in our view model. This is a new size, and in our view model we will have a property that remembers the sizes between renderings. So I call it last size. It will start it as just a 1 size, but each time it changes, I will first of all check if the last size is the same as the new size. Then we do nothing, just return. Otherwise, we say that last size equals the new size. And we want to somehow update the image. Right now, updating the image is just render a new version of the image that is of the correct size. So we will say that the image value equals we call old method, but with our last size. I also want to use this size as our initial size on an image. And the last thing we have to do is make sure that our image canvas actually fills the whole screen. And now if we resize the window, we see that it resizes, but it does skew the image. So that's the thing I want to fix next. And to fix the scaling issue, I want to create a little helper class, and I will just call it scene, the pre-data class. And this will take in a rectangular for our current zoom state. And the actual canvas size. And here we will pre-calculate some constants that we need for the scaling. First, we calculate the ratio of the canvas, or the aspect ratio. And we do that by saying the canvas size width divided by the height. And then we do the same for the selected zoom ratio. And I always want to make sure that the zoom rectangular is always inside, always rendered completely. So if depending on how good these ratios match, we have to adjust what we actually render. I will do it by saying dx. So if the zoom ratio is larger than the canvas ratio, I will just use the width of the zoom rectangular, else I will use the zoom rectangular's width by dividing it with the zoom ratio, and then multiplicate it with the canvas ratio. And I will do the same in Y. But here, if the zoom ratio is larger than, we will use the height divided by the zoom ratio wrong times zoom ratio divided by the canvas ratio. So it's the opposite of what we did for the X, and we remove this. Otherwise we use the zoom rect height. So depending on if it's X or Y, we kind of do the opposite. And now for X, we will calculate the actual top left or top right for what we want to render. So the left side will be the zoom rect top left, which is the left part of the zoom rectangle. And then we will add the adjustment factor that we calculate by zoom rect width minus the adjusted X divided by 2.0. This should be minus this should be the X. And we do the same for the right side, but here we add the adjustment factor instead. And similar for the Y. So we calculate the top Y to be the zoom rect top left. This has to be the bottom right. Y plus zoom rect height minus the adjusted Y divided by 2.0. I use 2.0 here, so it will actually end up as a double when we're done. And similar for the bottom. We use the bottom right, and instead we do plus. There. And now we can create a function here to use to actually scale from a XY coordinate in the canvas. That will be from 0 to 1 to a 0 to 1 in our render space or inside the area that we want to render. So take an X and a Y, and we will return a pair of bubbles. So that will be our coordinate after scaling. And we will scale by saying that the scaled X will be an interpolated value between the left X and the right X with the value of X. So that will take the X value in the canvas, kind of, which is scaled to be between 0 and 1, and scale it to somewhere between left X and right X. And now we do the same with Y, but we take the top Y and the bottom Y, and then we return oh, says yes. And this is a function that we have in the Mandelbrot file. It's private. I will make it accessible from outside so we can use it. And this should of course be a Y, and this spelling I want it to be the dy, not the dxy. And looking at this code, I actually see that we need to adjust from the top left even for the bottom, because we do kind of moving to the center and back. So here we move to the center and back up, and here move to the center and then down. And the same for X, so it should be top left on both of these. So now let's try to use our new class in our view model. So I have to create a few new properties here in our view model. First, I want initial zoom state. This gives a hint that we want to add zoom functionality soon as well. But we will start at rect 2.5. That's an offset. Negative 2.5 as a float. Negative 2.5. And import it. And the bottom right, we will do the same, but remove the negatives. These are kind of the numbers that we have in our old scale function in the Mandelbrot method function. And we will also have a private var that is a current zoom state. Yes, current zoom, which will start as initial zoom state. And let's have our scene. It would be a scene from current zoom state to our last size, but has a size instead of an int size. And we also have to create a new scene every time that the size changed of the canvas. I will put it in here in the update image, and then in the image function I will take it and move it into our view model, make it private, and now we can use our zoom or our scale function here. So the xs xy is a pair, ys is a pair that we get from our scene if we scale the x and the y value. And then we can send that into our Mandelbrot instead. Like that. And we also have to remove this old scaling that we have had before. And just use x and y that we get sent in. And that makes us able to remove this old scale function. And now when we resize our window, we see our image being rendered and scaled as we were expecting. And now I want to add the possibility to zoom. I want to be able to zoom in by doing a rubber band function. So I want to be able to select by dragging the mouse over the image and tell which part I want to zoom in on. So let's add a few things to the GUI. First, I will create a box around the canvas. And that is so we can stack components on top of each other. So we have the image canvas, and on top of the canvas I want to have a new component, drag selection, that will be another function, and put it here, and it's just it's a composable, and inside here I will do a new box that have the modifier fill max size, so it will be the same size as the window, just as the image canvas. And inside here I want to draw with the content, so this just gives us a handle to a canvas that we can draw on, kind of temporarily. So if we were to have a rectangle up here, let's say offset 10, I have to be floats, I guess, and offset 100 and 100. So we can actually say draw rect in here. Let's say color a blue one, and we have the top left equals the rectangular top left, and the bottom right, no, the size, I guess, equals the rect size. And I want to style it, and this is stroke width equal 1 float, so it will draw a rectangle of the size that we said here with a width of the line as 1 pixel wide. It's like this. And now we want to make it so we can move it with our mouse instead. So we add something called the pointer inside here, pointer input. I'll just say on the unit. So we can detect drag gestures in here, so we can also use it on touch screens and such. And the first thing we want to do is say on drag start. So this is when we start to drag something. We give it a lambda, say the position that we get from this. We want to put this position up in our rectangle that we want to later paint, but for compose to understand it, we have to make it a remember variable instead. And it will be a mutable state of this one, and I will start as null. So when it's null, we don't paint anything, and that means that inside here we actually have to say rectangular value and check if it's null, and if it's not null, we do that. So this makes it null safe. Like that. So now when we start to drag, we can take that position and update the value. So I will just create a new rectangular here with the position, and the size will start at 0. Let's also check the drag end. So on drag end, we will just take rectangle value and set it to null, so that is a signal to stop rendering it. And here we are not interested in the change, but the drag amount, we will actually say that the rectangular, if it's actually null, we don't do anything because we're not dragging. But if it's not null, we will update the rectangle again, kind of doing this. But we will use the old rectangular. It's actually the top left corner. And the new size will be the old size plus the drag amount. There is no additions on sizes, so we create an extension function for that. It will be an offset, and it will return an offset, or more, it will return a size. So we will just return a new size with this punct width plus the drag amount punct this point with the drag amount of y. And now if we drag our mouse, we get the rectangle that we can render. This should of course be height. And here we get an error because I was dragging. If I drag down or right, it works, but as soon as I go up or left, we get an exception because we can't render a rectangle that is smaller or negative. So to fix that, let's make a few methods here that calculates the actual top left using the rectangular, and I also want to actual size using the rectangle. We just create these functions. The actual size will be the size of the absolute value of rect point width and the absolute value of rect point height. This is a built-in Kotlin function for absolute. And the actual top left will be offset. Where we, for the x part, will make the min value of the rect top left dot x and the x plus the size width, and we do the same in y. And this would be the float version. And we can also do this. So now if we render, we can drag in both or all directions. So to actually zoom in our Mandelbrot, we have to make something happen when we do the drag and thing. So on drag and, if we do this, just to check that we are actually dragging, that is, that rect is not null, and do that thing, we will call a method that say on select, and on select will take in the rectangular from or actual top left of the rectangle we are working on, and the actual size of the rectangle. And this on select function we will take as a parameter, and it will have the type of rect to unit. And we will add that method to our model. So we will have an on select. We will call it like this. And we create it. So on selection, we have to recalculate what's top left and bottom right of our newly selection, or our new zoom, let's say. So the top part, let's call it A, will be the scene scale. And we will scale the selected area, the left of it as a double, and we divide it by last size, which is the canvas size, by the width of it, and we took the selection top by last size height. So that's the top left part of the selection inside the Mandelbrot realm, so to say. And we do it the same for bottom part. But there we take the right side and the bottom part, and then we calculate a new zoom state, which is the rectangle from AX as a float to BX, BY, no, AY as a float to, let's take this, but with a B. So that's our new zoom. So I will just say that the current zoom equals zoom, and update the image. And now if we drag and release, we zoom in on the area that we select. One thing about this is if we keep zooming in, we will hit a limit where it turns black. I have not debugged this, but I think it's where double can no longer hold the values that we are working with. And now, as the last thing, let's add a button to the GUI so we can reset back out to the max zoom. So button with the text. Reset, and on click we will call our model and just say reset, create that method, and on reset we just say that the current zoom equals the initial zoom, and update the image. And if we now run this, we have a new button. So if we zoom in some and click on reset, we move out again. And that's where I will leave this today. Thank you for watching, and goodbye.